Hello and Assalamu alaikum students. Here are some uh, useful probability approximations. It means that we can use one probability distribution model to estimate probabilities in a different probability distribution. So some of the useful ones are binomial to hypergeometric approximation. In this approximation, we can use the probability distribution model of binomial distribution to estimate the probability in hypergeometric distribution. And similarly, we can use Poisson probability distribution model to estimate probabilities in binomial distribution. And normal probability distribution model can be used to approximate probabilities in binomial model, and similarly normal can be used for Poisson probability distribution. Here you notice the word approximation. It means it is an indicative of the fact that when we use different when we use different probability distribution models, or when we use one probability distribution model, for example this one, to to calculate the probability in a different distribution, it is not the exact value, it is an approximation, right? So we can approximate the probability values in one probability distribution with the help of another formula. Sometimes it is useful when we are unable, it is difficult to use the actual one, then we can make use of the other one, which we feel easier, and also it is applicable, and these approximations are applicable under certain conditions. So we'll see those conditions also. Is binomial to hypergeometric approximation. We know that the formula or the model for hypergeometric probability distribution is this one, and for binomial is this one, right? So we are pretty familiar with these two formulas or functions or probability models. These are different names for this. And for the approximation in which we can use binomial, this formula, to estimate or approximate the probabilities in hypergeometric distribution, we have a condition that says that we can apply this approximation when n over n, means small n is the sample size and capital N is the size of the population, or the whole lot of the manufacturing process, means all the products in the manufactured lot, and n is the number of samples that we have chosen from that lot. So if this fraction is less than or equal to 0.1, then we can apply binomial for hypergeometric in order to get a good approximation. Okay, if this condition does not met, our approximation will not be adequate and we will have huge margins of, means we will have huge errors in our approximation. Okay, how we can apply this approximation then? So when this condition is met, means small n over capital N is less than or equal to 0.1, then we can approximate hypergeometric probability using binomial probability model, just by replacing this p with d over n in the binomial probability distribution, like this. So we just replace p with d over n in this formula, and then we can apply this formula for these conditions here, because here we are using d, right? D is the value of interest or the defective pieces that we are finding in our in our samples. Okay, so we simply replace this p in the binomial, which is the success rate, with d over n. D over n is the ratio of the defective models to the actual population. Okay, simply by transforming this model to match the variables of hypergeometric probability distribution. Poisson to binomial. So again we will revise the models, probability models for binomial and Poisson. This is for the binomial and this is for Poisson. Now we can use Poisson's model to estimate probabilities in binomial distribution. You can see that there are some differences. We are not using n here, we are using lambda here and x here. X is common, but there is no n or p here, so we will have to apply some transformation to the formula, replace some variables with more suitable ones. So to apply the approximation, the condition is that n, or the sample size, must be large and the value of p must be small, and typically we consider this approximation to be adequate if p value is less than or equal to 0.1. okay, means this p value should be less than or equal to 0.1. Then if this condition is met, then we can approximate binomial probability using Poisson probability distribution model by replacing lambda in this formula by n times p. okay, n and p are the variables which we get from the mathematical model of binomial probability distribution. okay, we simply replace this lambda with np in this formula, and we can use this to calculate probabilities in binomial distribution, and our approximation will be adequate if these conditions are met. So once we put this value here in this formula, we get this transformed mathematical model, or the probability distribution model of Poisson, to apply it on binomial. okay, our next one is to binomial approximation, and we know that the mathematical model for binomial is this, and for normal is this one, and in order to apply a normal for binomial, the condition for to have an adequate approximation is that the n, or the sample size, must be large, and typically we consider that it is actually experimentally observed that when the values of n, or the sample size, is larger than 10, means our sample consists of 10 measurements. okay, or we have chosen 10 samples out of the lot, or more than that, and our values for p are typically smaller than 1 over 2 or 0.5, then this approximation gives us adequate results. okay, but in general, the larger the value of n is the better, and the smaller the value of p gives us better approximation. okay, and how we can apply this approximation now? When the condition is met, when this condition is met, means n is very large and p is very small, then we can use normal the formula for normal on on binomial by replacing mu with np, n times p, and sigma square, or the variance, by np into 1 minus p. We replace these values in the formula of normal probability distribution, and then we can apply it on normal. Once we do that, this is the formula that we get. Simply replace sigma, this sigma square was equal to np times 1 minus p, so sigma will be equal to square root of np times n minus p. So we replace this sigma with this value here, so 2 pi was already there, we get this one, and mu is replaced with n times p here, and sigma is this. So we get this value, this transformed formula, to apply it for approximation of normal on approximation of binomial with the help of normal. Now you know that normal probability distribution is a continuous probability distribution, while binomial is discrete probability distribution, right? So in order to apply that on binomial, we have to make continuity correction also, because binomial is discrete and normal is continuous. So we have to make continuity correction. How can we do that? You know this formula, right? This is the standard cumulative probability function, right? For normal probability distribution, here in the general one is actually x minus mu over sigma, right? But when we assume that the value of x is that when we are estimating the probability for the value of x is equal to a, then we replace x with a here, okay. And mu, we know that mu is equal to np, right, and sigma is sigma here. So in order to do the probability continuity correction, or to do that, we we extend its value actually by adding and subtracting 1 over 2 to a, like this. Here what we are doing is we take this value exactly like this, okay. We add 1 over 2, okay, so we get a probability for this one, minus, we do this, we subtract 1 over 2 from a, and we get this probability value of the probability from this, and then we subtract it from this one. So if you plot a normal probability distribution bell shaped curve, and you locate the value of a plus 1 over 2 and a minus 1 over 2, then you will realize that we are extending the region in order to make this distribution continuous, because in binomial it is just a straight line, single line. So what we are doing, we are extending it one half forward and one half backwards. By doing this, it will give us a region. You remember that in continuous probability we need a region to perform integration on it, okay, to find area under the curve for probability, right. But binomial is only a single line, it does not give us one area. So in order to get that area, we increase 1 over 2 and decrease 1 over 2, means half forward and half backward from a, and we get a small region upon which we can perform integration, okay. So this is called as continuity correction. So if this was actually for one value, now we can have an interval also, right. So that interval is written like this. So if the value of x already varies from a to b, then we can use the value of the last value, means this was the last value, right, on the positive side. So this is b plus 1 over 2, and here we replace this with a, the first value, okay. So this is for the interval and this is for the single value, okay. Now we call this one equation a, because we need to use it on the next one. Use it for sample fraction defective. What is sample fraction defective? It is actually represented with p with a small hat on the top. Do not confuse it with this p. This is different and this is different. This is a fraction, x over n. X is actually the number of defective parts in the sample. Sample is n. You know that sample size is represented with n. So if the sample size is 10, and from that sample there are 2 defective products, then it will be 2 over 10 and p will be equal to 0.2, okay. That is called as sample fraction defective, means the defective products in the sample. So for this one we can also modify our previous formula for sample fraction defective, because this p hat is also a random variable, like the variable x we can estimate for this one as well. So once, if we want to do it for this sample fraction defective, then what we do is we divide the mu or mean by n and sigma or standard deviation with n also in the previous formula. I remember that phi is equal to mu minus n over sigma, right. So from there we got the standard normal distribution function, right. So in the equation a, we will simply replace mu with mu over n and sigma with sigma over n, and our equation will become like this. The equation a, the last one on the previous slide, this was v plus 1 over 2, this last one, minus p. Why p? It was n times p earlier, so it was mu was equal to np, and when we divide mu with n, so we get np divided by n, it cancels out and we get this one. And similarly it was sigma here, and we can put this value of sigma, divide it with n, and we get this value. Okay, and similar is the case for the next equation. It was a for the next term, so it was a minus 1 over 2 minus np divided by np times means the square root of np times 1 minus p. So we divide both by n, and this is what we get. So the derivation is like this. Okay, this is the derivation for this one and for this one as well. So mu was equal to np, we divided it with n and we get p, and sigma square was equal to n minus p and 1 times np times 1 minus p. So when we want to find sigma over p, we do this calculation. Okay, this is a very simple one. I believe you can understand it very easily. Okay, so now let's move towards the next one, in which we can use normal for. So we can apply a normal probability distribution for estimating probability in Poisson distribution. Again, just revise these models for Poisson and normal probability distributions. We can apply approximation here when the value of mean or the lambda is large, and typically we consider it to be large when lambda is at least 15. Okay, so at least 15 means that if it is 15 or larger, then our approximation will be good. Means that when if we apply normal probability distribution model to calculate probability in Poisson distribution, and the value of lambda or mean is large, then we will get a good approximation. Okay, so how we can apply that? So in order to apply that, we replace mu with lambda and sigma square with lambda in normal in this one. Okay, so we will replace both of them with the value lambda, and this is what we get. Okay, so this is the formula that we can apply after transformed formula of normal probability distribution that we can apply for calculation of for approximation of probability in Poisson distribution. Okay, and that's all for today. If you have any question, we can discuss it later on whatever medium you want to use for communication. Okay, thank you very much.